Good evening, all. 6 o'clock. Let's get started for tonight. We were supposed to review lecture 17, which is like commonly used digital component. Uh, I saw a couple of questions over the discussion and I have replied them already. Apart from that, if you have any question, let me know. Because, all right, let me give couple of pointers for these components that we are discussing in this lecture, lecture 17. So we mainly focused on two components. One is decoder and other is multiplexer. Very, very important component inside computer, inside a processor design, logic design for a processor. So these components are almost like a heart of any processing system. You'll realize that in 147, when we actually go and implement a processor from scratch in that course, 147 computer architecture, you'll see that we use like many places multiplexer is used, and multiplexer, one of the important component inside the multiplexer is decoder, right? So let's discuss about them a little bit and do some problem around that, those components. Let's see. So so if you look at that definition of the decoder, so we are talking about two components. One is decoder, and other is multiplexer, or in short, we call it a MUX, multiplexer or MUX. So a decoder definition is like we have a digital component which has n input, and m out, any digital component, okay? And but it has to maintain a relation. So this is a decoder. It has to maintain a relation which is n less than equal to m less than equals 2 to the power n. Right? So these characteristics, this condition must be met so that we call it a decoder. Now a specialized component or specialized classification of decoder, specialized classification of decoder is line decoder. So line decoder is basically mostly used, like whenever we talk in the processor design, when we talk about the decoder, we usually mean it's a line decoder. Okay, so line decoder is a decoder, it's a decoder. So that means it can have n input and m output. Okay, but in order to tell it a line decoder, that's this m output. Like let's say we call it output 0, output 1, output 2, output 3, output m minus 1. They will be 1 and only 1 will have logic value 1 at any point of time, or I shouldn't say point of time there, that doesn't make sense. It's basically what I wanted to mean is that when value uh, at any given combination of input. So in the incoming side, there will be this different combination of inputs in terms of logic bits, like logic value 0 and 1. For any given combination, there will be one and only one have logic value 1. That means also all 0 is not a valid output. So it has to be at least one of the output has to be 1, and only one output can be 1 for any given combination of the input side. That's the line decoder. And also one side note, when we usually in the logic design scenario, when we tell it's a line decoder, we usually tell it a n by 2 to the power n line decoder. Usually, okay? That means like you will see either 2 by 4 line decoder or 3 by 8 line decoder or 4 by 16 line decoder, 4 cross 16 line decoder, something like that. Of course, you can build like, for example, 3 by 6 line decoder. It's possible to build up that. But these are kind of a standard design component. And what is meant by that, a standard design component, is that we use it to solve many problems. For example, like this. Let's say you want to build up a function like, let's say A, B, C, D, E, F. Like this function is a 6 variable function, right? A, B, C, D, E, F. Yeah, 6 variable function, which means it will have 64 different combination of the input. Like in the truth table, you will have 64 rows. So let's say this function is defined at 0 to 14, 31, 54, 59, for example, right? And you want to build that circuit, logic circuit. Of course, on the paper pencil, you cannot actually optimize this function because K-map technique is limited for, like, at least from human perspective, it is limited for 4 variables. Beyond 4 variable, it is not possible to build up a K-map table that humanly comprehensible. Okay, we can definitely write a software program along that steps to define that, and that's in fact like billion-dollar industry by itself to optimize multivariable function, Boolean function into an optimized logic circuit. And there are many advanced algorithms have been developed. But starting from the K-map technique, that is the very stepping stone. But there are many advanced algorithm and techniques that actually allow us to build enterprise level software whose sole purpose is to solve like multivariable logic or logic function into the logic circuit gate. Here I'm talking not only 6, 10 variables, I'm talking about 100 variables there. Okay, so, but let's not go into detail onto that, out of our scope. But our main problem in hand here is this. We have 6 variables. We cannot deploy K-map. How do we build this circuit given this SOP? We can use this component 6 cos 64 line decoder. So it will have like 1, 2, 3, 4, 5, 6 inputs, and let's say its input terminals are marked as like I5, I4, I3, I2, I1, and I0. So I0, and we connect input side like this: A connected to MSB. Why? Because in this sequence, we kind of assume this is MSB, this is LSB kind of stuff. Okay, and that's how these standard SOP mean terms index are determined. Indices are determined. So that's why it is MSB, LSB. So A, B, C, D. This is very important that we mark the inputs in terms of indices, MSB, LSB, and clearly mark which variables is connected to which terminal of that line decoder. And then our life is very simple. You have this different mean term output out of this line decoder. So what you all need to do is use the mean term output M0, M2, M14, M31, M54, and M59. These outputs, we take them and run it through giant OR. This becomes like 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4, 5, 6. So it becomes a six input OR, and you have this 6 variable function implemented. Okay, so that's the beauty of using this kind of standard component, that it will rescue in the situation where you cannot actually do a optimization handy, or at least you don't have a constant not to use line decoder, right? If you have a constant that, okay, you don't have line decoder, then what you'll do, you'll actually you can do something about that with this concept. With this concept, you can do this thing, right? You can deploy internally the decoder kind of technique, where we basically, you can have like each variables like complement form as well. Then this is the matter of combining them, right? This is 0 is like A bar, B bar, C bar, D bar, E bar, F bar, right? This is M0, right? Like M2 is basically A bar, B bar, C bar, D bar, E, F bar. So that means what we are talking about here is an AND gate for the M0, which is taking A bar, B bar, C bar, D bar, E bar, and F bar, right? And this becomes your M0 term. So practically you see that we are constructing a part of the decoder, part of this decoder in our mind to do that. If we are not allowed to use a line decoder directly, but at least we can use that concept, right? And then for the M2, we can do the similar thing like a big giant and with A bar, B bar, C bar, D bar, E, and F bar. This becomes your M2. And you can just derive these M's, this minterm, accordingly, and OR them, right? And OR them. Not them. So this is another way you can actually uh, take help of this decoder concept to construct a given function, Boolean function, into a digital circuit if there is no scope of optimization, or at least you cannot do it on the paper pencil using the techniques that you know so far. Question? Okay, now let's talk up a little bit on the multiplexer side. So multiplexer are the component where it's basically it's analogous to switch and case statement. Let's say I hope you guys are familiar with this kind of high level language construct, like switch on the variable A, switch on the variable A value 10, you do some action, case 11, you do some action, etc., and default, right? Switch and case statement. This is basically like cascade of if-then statement you can think of from software perspective. Multiplexer are nothing but a switch statement at the hardware level. So is a switch case statement at the hardware side. Okay. So what does it mean really? Is practically saying that, let's say I have like 4 input coming up, I3, I2, I1, and I0, and I have a selection bit, S1, S0. Okay. So what practically this guy is telling is this: switch on S1, S0. So we're looking at the value of S1, S0. So this is S, you can think of S, right? Switch on S1, S0. Case 0, Y equals I0. Case 1, Y equals I1. Case 2, Y equals I2. Case 3, Y equals I3. So practically this is an if-then selection or decision-making component on at electronic circuit level or logic circuit level. This is an like selection or decision-making component for us. To build this component, we need internally a decoder. Let's say we have, in this case, 2x4 line decoder. S1, S0 is connected to I1 and I0 of that line decoder. And it has these output like M3, M2, M1, and M0. They are basically your minterm, corresponding minterms. And then you have these 4 lines to select from to route to the output side. Okay, so this one, I3, is ANDed with the M3. Okay, and then M2 is ANDed with I2, and M1 is ANDed with I1, and M0 is ANDed with I0, and all these things are ORed together to give you the Y. So my component boundary is not this, but it's more like this. Okay. So in this case, what will happen? Like, let's say I have, let's say 0, 0, right? In that case, your M0 will be 1 and other outputs will be 0 from the line decoder side. That means 0 and this output and output will be 0 except for the last one, which is connected with the M0 itself, and then its output will be whatever the I0 is, right? It can be 0 or 1. That means Y in this case will become 0 or 0 or 0 or I0. So in fact, this is I0. Now let's say you change it to 1, right? So in that case, I'll have M1 as 1 and M0 as 0. So that means ultimately I will have this output will become 0 and this output will become I1. And therefore, your Y will become 0 or 0. That will become 0 or 0 or I1 or 0, which is I1. So that's what is meant by selecting input like incoming input like I1, I2, I3. You are selecting between them. What's the significance of this? What is the selection about? Like for many students, I have seen you guys have some concept that, hey, this is nothing but some logical function, right? Why is a logical function? Why are we saying that this is a selection? It is just a bunch of logic evaluation. But look at this way, right? In the computing system, it is always a multi-bit information. It is not a one-bit information. Let's talk about like a 4-bit information, for example. Okay, 4-bit information. So what if I have a multiplexer? Let's mark the input I1, I3, I2, I1, and I0 in selection 0 and 1, and output Y. Now the twist here is that these are not single bit input. Let's say these are 4-bit input. So that means each of these bars is actually representing a value, like 4-bit value, right? So let's say the incoming values are, for example, like maybe they're representing 5, this is representing 10, this is representing 12, and this is representing, say, 1, right? And your output is as well a 4-bit. Okay, so that means if you are actually putting out 0, 1 here, that means we are selecting I1. That means my output is going to be 12. Now you switch this guy, let's say 1 and 0, 1 and 0. That means in this case we are selecting 2. We're selecting 2, right? That means my output will become like 10 here. So it is not really like, it is internally, it's a logic evaluation, of course, but at least the function level, top level, macro level function, it seems to be we are selecting between the values. And that's what gives you programmable capability within the hardware. We'll see it more on the 147 computer architecture study. Questions so far?
Can you change the page on the Jamboard to 16? Thank you.
Sorry, Christopher. My bad. My bad. My bad. So whoever, if someone missed it, so what I was telling is that depending on the selection of this multi-bit multiplexer, right, where its input is not one single bit, it is multiple bit. In that case, we are practically selecting a value. Though it is internally, it is evaluating the logic and everything, but at the macro level, we are selecting between values, and that's what gives the programmable capability inside the hardware through the multiplex. Another question is, how do we build it? What's the internal of this? This is built by like 4. So this is 4-bit, 4x1 mux. So what we can do, we can actually use 4 1-bit. So it is like 4 1-bit 4x1 mux. So that means each of them has 4 input, 4 single input, single bit input. And these outputs are then connected like form a bus, 4-bit bus. So this is your Y side. And this is like more like individual bits of these 4 bits, right? Individual bits. So this is, let's mark them. Maybe we'll mark them as a, how do we mark? Okay. Maybe it's D3, data 3, data 2, data 1, data 0. Okay. So this guy is D3 bit 3. This is D2 bit 3. This is D1 bit 3. This is D0 bit 3. For this multiplexer is connected with data 3 bit 2, data 2 bit 2, data 1 bit 2, and data 0 bit 2. This one is data 1 bit, data 3 bit 1, data 2 bit 1, data 1 bit 1, data 0 bit 1, and this one is data 3 bit 0, data 2 bit 0, data 1 bit 0, data 0 bit 0. That's how the connection is. And as far as the selection goes, selection 1, selection 0 bits, they are common between these multiplexers. So they are basically your single S1 and S0. They are being fed into these selection bits common to them. And that's how this multi-bit multiplexer is implemented. Question? Okay, if there is no question, then let's do one problem. Okay? Or maybe we can take a break. 6:35. Let's come back in 6:35, and we'll do some problems and so on and so forth. Okay, 5 minutes done. Let's come back and let's do some pop quiz. Please go to your canvas and find out pop quiz 6 and hit yes in this poll when you are ready for entering the passcode. Okay. Okay, we have 35, 39, 36. Maybe a couple of more seconds I'll wait and I will pass the passcode poll. Okay, here is the passcode. Let's see.
Professor,
Yes.
I'm putting in the password and pressing submit, but it's not like letting me enter the quiz. It's just taking me back to like, it's basically reloading the page.
Hmm. Can you restart your browser and try it again?
Yeah, it's still not working.
I don't know what to say. Is it a browser issue? Can you change the browser to something else and try?
Yeah, okay, I'll try it on Safari. It's not working on Safari either. Is it the WIS password? Oh, it's an L. Never mind.
Okay, good to know. Thank you.
Professor,
Yes.
question 8, it's not showing an answer box. It just has the question, but nowhere to answer it.
I have
I'm
this
seeing the same thing, yeah.
for question 10.
Okay. Yeah, just skip that question and send me email afterwards.
Okay.
Okay, I think most of you are done with this quiz.
Professor, on number 7, I couldn't find any space to put my answer.
Yeah, I think some other also has a similar issue. So what I told, just send me the question number that you over email. I'll take a look.
Okay, thank you.
Okay, so this quiz, let me see the stat. Average score 53, high score 80%. Okay, we need to watch out about the average score. Anyway, now let's do a problem. Let's do a problem, okay? Let's say how many two input NAND gates are there in, okay, let's rephrase this. A 4-bit 8x1 mux is constructed using 2-input NAND gate only. So we use the universal gate NAND, 2-input NAND gate, to build a 4-bit 8x1 multiplexer. How many NANDs are there? So how many gates are there? Okay, so this problem, I'd suggest take 5 minutes yourself to do, and yeah, yes, take 5 minutes from now. So 6:55, I'll open up the break room for you to discuss in your peer groups this problem, then come up with the answer. Okay, and break room will be for 10 minutes. So 10 plus 5 minutes, 15 minutes. So do it now, this problem, yourself 5 minutes. Okay, I'm opening the breakout room for you for 10 minutes. Please discuss this problem with your peers and come up with a solution. Okay, let's wait for a couple of seconds for everyone to come back from the breakout room. Okay, anyone wants to go with the answer? Anyone, any group? No? Yes?
We got 184.
184. Okay, can you explain how did you get that? Yeah, I don't know whether it is right or wrong at this point, but let me hear your explanation.
We had 4 multiplexes, one for each bit. And then inside each multiplex, we used 46 NAND gates.
46
Since it's a 3 by 8 line decoder with
right.
8 inputs for the multiplexer.
Mm-hmm. Okay. Is there any other answers than that? Okay, let me try to deduce it, okay, and see, maybe you optimized for that. Let's see what happens. So this problem is basically, as I told, showed here, right? This is like 4-bit 4x1 multiplexer, right? So here we are talking about 4-bit 8x1 multiplexer. So that means we are actually using 8, instead of 1-bit 8x1 multiplexer, we are using 4 1-bit 8x1 multiplexer. So that means if we can come up with the number of NAND needed for one 1-bit 8x1 marks, then we'll just simply multiply that by 4 to get the answer. So this multiplexer needs like 3x8 line decoder, followed with 8 and, which we can say 8x8 into 2 NAND, and then followed by 8-bit OR, which we can deduce as this is equivalent to 7 2-bit OR, and each 2-bit OR we can deduce at like A or B is basically by De Morgan A bar B whole bar, which means we have 1 2 3 NANDs in it, in very crude sense. So that means it is 7 multiplied by 3 NANDs, which is 21 NANDs. And this is like 16 NANDs. Now, how about this one? This one has 2x4 line decoder and 1x2 line decoder, which 1x2 line decoder is nothing but a 1 inverter inside it, right? 1 inverter. And this guy is basically 1x2 inverter, 1x2 inverter, sorry, 1x2 line decoder, followed by 4 and, yeah, followed by 4 and then overall it will have 8 and. to combine output from here to here. So 8 ANDs are there. So we're talking about 16 NANDs there. Here we are talking about 8 NANDs and 2 NANDs. So this thing has total of 10 NANDs plus 1 NAND plus 16 NAND. So this one has 10 plus 1 plus 16, which is 27 NAND itself. So adding them together, 27, 16, 21. So we have total 27, 16 plus 21, which is equals 27, 37, 43, 43, 44, 64 NANDs. So it implies if we want to deploy 4 of them, so 4 multiplied by 64, 256 NANDs. Does it sound okay? Or Charlotte, you did optimize more on top of that?
No, I didn't calculate the line decoder correctly.
Oh, okay, okay. So that must be the reason then. Yeah. So 256 is the one that we do it here. Okay, any question? So if we don't have a question, then let's stop here at this point and see you all in next week. Good night, everyone.